Hey class, Adam Ward here. I want to work through a Streeter-Phelps example with you today. So in the example problem, we are given a plug flow stream with a velocity and a depth, a deoxygenation rate constant of 6 per day. Pardon the typo, that used to say 0.6 per day. This is an initial load of 10 milligrams per liter of BOD, meaning that the concentration of BOD at the point source, so after mixing, is 10 milligrams per liter, and saturated water at 8.5 milligrams per liter. So this initial load, what I'm trying to describe there, and perhaps poorly worded, is this L naught, the BOD concentration at x equals 0. We're given a saturated oxygen concentration. And so task number 1 is to generate a plot of BOD, DO, and deficit through distance. And so to do part 1, what you can see I've written down here is our Streeter-Phelps model for a point source. So we've got a BOD equation and a deficit equation. We'll add to that an oxygen equation, and that's of course just converting deficit to actual oxygen concentrations. And so this is the model we need to build. What I'd like to do then is go through and see, do we have the information required? And so just looking at the variables that we'll need, one of those is velocity. Now we're given velocity in meters per second. I've gone ahead and converted to meters per day. So I'm going to work all of my times in units of days in this problem. Why did I pick days instead of seconds? The rate constant was 6 per day. I've got to convert one thing or the other. And so I chose to convert velocities to days rather than rate constants to seconds. You should be able to do the problem either way and get identical answers. We need a KR, so we need a term to describe the removal of BOD from the system. And of course, that's the sum of decomposition and settling. Now, we aren't given a decomposition rate in the problem. We're given a deoxygenation rate. But of course, those are directly related to one another. As we remove BOD, we remove oxygen from the system. And so a deoxygenation rate, that's from the perspective of oxygen, but that's actually the same as a decay rate from the perspective of BOD. So we lose oxygen at the same rate that we lose BOD. So that KD is 6 per day. And we don't know anything about settling, so we'll go ahead and assume that settling is 0. Now we've got a KR. Looking at Ka, I went to Chopra. I looked up reaeration formulas for rivers. Given this velocity and this depth, that put us in the range to use the O'Connor and Dobbins formula. And so you can see I've written that out, 3.93 times velocity to the 0.5 divided by depth to the 1.5 power. I get I get an answer, of about 2 per day. One thing to note here in particular is the units. So in this equation, and you could look this up in your textbook to remind you, you put velocities in meters per second. You put your length scale in meters, and what comes out is Ka in units of per day. So buried in that 3.93 term is what I often refer to as that empirical unit magic, right? Although the units for that 3.93 aren't shown, you've basically got to assume that it has all of the correct conversions with it, so that you plug in meters per second and meters, you get out units of per day. Let's see. Other terms we need. DO, so the deficit at x equals 0, that D naught term, we're going to assume that that's 0, meaning right before this point source and mixing, that water was completely saturated with oxygen. And so if you go ahead and now take the equations on the left-hand side of your page and actually solve them, I've gone ahead and plugged in values of x starting at 0 and plugged in every 1,000 meters to generate the plots that you see below. This is part 1, a plot of DO, deficit, and BOD through space. The y-axis on there is concentration in milligrams per liter. And so in blue, you can see that exponential decay of BOD. In red, you see deficit starting at 0, growing into some peak value, and then decaying away. And you see the oxygen term then is the saturated level minus that red line. That gives us the green line, that's DO. So point 2 is to identify where reaeration and deoxygenation are equal and the minimum in-stream DO. So the point when reaeration, or the addition of oxygen, and deoxygenation, or the removal of oxygen, are perfectly matched is the low point in that DO sag. Right? It's when the time rate of change of deficit is equal to 0. And so graphically we can already look at this and we could estimate that critical location, XC, critical oxygen concentration, OC, and critical deficit, DC. And those are all labeled in purple on the graph. A couple other things to point out, just to give yourself a gut check and make sure that this model is working correctly. The blue line starts at a value of 10. That's good. That's where L naught should be, labeled in red. And I've got my saturated oxygen level shown with a horizontal gray dashed line labeled OSAT. So graphically we've got the answers. We can do better than just estimating off of a plot. And so we want to explore the critical conditions in this problem. Now for the case where initial deficit is 0, we've got an equation in Chopra that looks like this. So we can calculate the critical time, or the travel time until you reach that critical point, as shown here. And so if we plug in the values we have of 2 per day for Ka and 6 per day for Kr, I come up with a critical condition occurring about 0.27 days of travel time in the network. That's a time. The problem actually asks you for a location. And so we know that critical location could be calculated as the velocity multiplied by critical time. So when we work that out, I get about 7,233 meters. Here's our example problem and our results again on the right-hand side of the screen. And you can see that that critical location plots about as expected, and so I feel good about that calculation. Critical deficit, again, this equation comes from Chopra. This is for the special case where D naught is equal to 0. And we can plug in values for our KD, our KA, and our L naught. And when I go through that calculation, I get a critical deficit of about 5.77 milligrams per liter. Now that critical deficit, that should be the top of my deficit curve, or that peak location. And you can see I've labeled that in red, critical deficit at about 5.8. Perfect. Finally, critical oxygen, that's a simple arithmetic. We get a critical oxygen level of about 2.88 milligrams per liter. So that's the minimum oxygen we create in the stream. Again, labeling that in red so you can see where that occurs. Again, I like to double check my plot against my calculation to make sure that I haven't made an error somewhere. And so I feel pretty good about how this is going. Now the final problem here was, at what location or what time do we achieve 50% and 99% removal of that BOD? There's two ways you can approach this problem. One would be to use the Streeter-Phelps model equations. So they were on the previous slide in the bottom left, that L as a function of x and D as a function of x. You could actually solve those for either the time or the spatial location where you achieve a certain removal by plugging in, for example, 0.5 equals 1 for L naught times e to the minus k over u times x. Or we can use the shortcuts that we learned previously where, for example, half-life, or that T50, is 0.693 over lambda. Now that lambda was the sum of all the removal mechanisms. In this problem, the only removal mechanism for BOD is decay, Kr, or Kd. And so we can simply use that shortcut and say, well, time of 50% removal is about 0.11 days. Or using velocity to convert, that's about 3,000 meters. And again, I just want to double check this on my plot. So if I go to the concentration, that is half of what I started with, so 5 milligrams per liter, and I'm showing you this in purple lines, move over to the curve, and then down to the x-axis. 50% removal, about 3,000 meters, feels good. We can do the same thing for T99. That's 4.6 over lambda, and we ultimately conclude about 20,000 meters. And again, showing you in purple where that is, that's about 99% removal. Seems to fit with our model. So, having watched this example, you should be comfortable formulating the Streeter-Phelps equations to develop profiles through space of BOD, deficit, and dissolved oxygen. You should be able to analyze those equations and pull out some information about critical points, so the time or spatial location where you reach minimum oxygen, maximum deficit. You should be able to calculate times when you achieve certain removals of BOD from the system, and be able to formulate the equations associated with extracting those. So basically what we've done on these last two slides. I hope this helps you see how the Streeter-Phelps equations can be used downstream of a point source. The next complication that we'll add will be distributed sources of both BOD and deficit. And so stay tuned for the next example and the next lectures based on that. Thanks for sticking with me, everyone.